Okay, consider this. We have this young lady has a bucket of water, and let's see what she's going to do with it. The key here, I hope you have noticed from the video, the water does not spill over, even though at some part of the trajectory of the bucket is upside down. Let's repeat this again. Pay attention to the fact that the bucket is going to be upside down and sideways as part of its motion. Now, the question is, how come? How come does the water not spill even though we have a bucket that is upside down? Okay, let's look a little bit at a schematic of a bucket and the water in it when it is at the top. So it is upside down with the water not falling. Okay, let's examine the situation of the water. What's its velocity at that instant? Its velocity is like this. If there are no forces acting on the water, it will continue on a straightforward motion. That's Newton's first law of motion. However, in this case, we have forces acting on it. Among the forces that we can think of, we have the bucket here, the bottom of the bucket, but it is on top here. It's going to be exerting a normal force acting on it this way. And then there is, of course, the gravitational force acting on it this way. These two forces are perpendicular to the velocity. So their effect is to change the direction of the velocity. In this case, to make the water follow the circular path. The normal force due to the bottom of the bucket and the gravitational force, they both of them combine in this particular case to provide the centripetal force responsible for keeping the water in a circle instead of allowing it to fall. Let's look at this other example. Here he uses a coat hanger to get a penny to go around in a vertical circle. See there, it's pretty good. The penny does not fall. Same thing. In this particular case, when the penny is on the top, coat hanger is going to act on it from the top, providing a normal force, and then there is the gravitational force. Now the combination of both, in this case, also provide the centripetal force. Now, if the circle was a horizontal circle, instead of a vertical circle, of course, the gravitational force would not be providing part of the centripetal force. It is providing part of the centripetal force in this case because it is just perpendicular to the velocity at that particular point. Let's look at this other example. We have cars and motorcycles spinning along a vertical wall. So this is quite an interesting show. I have never seen it in person. But when the car is on a vertical wall, this is the way the car is. The wheels are on this side. What are the forces acting on the car? Gravitational force straight down. It is not falling down. It's not accelerating in the direction of that gravitational force. So that tells us there must be a force balance in that, and that's most probably static friction. However, the car is moving with a velocity this way that is changing direction along a horizontal circle. The horizontal circle is perpendicular to the platform here. Now, the force responsible for changing the direction of that velocity must be the normal force acting on the car, on the tires of the car, due to the vertical wall. Now that normal force is unbalanced and there is no other force acting along that direction. So in this particular case, for this horizontal circle along which the cars and the bikes are spinning, the normal force is going to be responsible for our centripetal force. Just to make sure, for example, when we have a satellite going in orbit around the Earth, in that particular case, the satellite is in a circle around the Earth because of the gravitational pull of the Earth. In that particular case, the only force acting on the satellite is the gravitational pull of the Earth. And it is that force that's responsible for changing the direction of the velocity of the satellite. So in that particular case, the centripetal force is due to the gravitational pull of the Earth.